Hello and welcome to this evening's Core Science Physics Hangout Part 2. We're going to cover the second part of the physics course and I'll just start in 1 minute time. If you're from Nodeswood and you're watching, feel free to put your name on the frog page. Okay, let's get started then. This Hangout covers the second half of the physics course. I've also done one for the first half, so you can go and watch that. We're just going to start off with a little bit about energy, because we didn't get around to doing that on the last part of the topic. So first of all, it's really important to know that energy cannot be created or destroyed. So you can't make it, you can't destroy it, you can only transfer it from one type of energy to the other. For example, in a kettle, you may have the energy transfer whereby you have electrical energy, which is then transferred to heat energy. Or for example, over here with this solar car, you will have solar energy or light energy transferred into perhaps either kinetic energy, if that causes the car to move straight away, or more likely into electrical energy, which then might help move the motor and things like that. So these energy transfers that go on are really important, but it's also important to remember that energy is not created or destroyed. So the types of energy that you need to be aware of for your P1 exam are all of these listed below. So electrical, light, sound, kinetic, which is all to do with movement, nuclear, heat, chemical, gravitational potential, and elastic potential. So these ones here, they must include the word potential, and they remind you that they're a stored kind of energy. So with energy, you can look at energy efficiency, how efficient an appliance is, or some sort of energy transfer is. And this is the equation that you get on your sheet. You'll get the equation that says efficiency of something equals the useful energy out divided by the total energy in times by 100%. So for example, if you were looking at a kettle, if you said that 50 joules of energy were useful joules, and the total input of energy was 100 joules, you would be looking at that kettle being 50% efficient. If you did 50 divided by 100 times by 100%, that would give you 50%. So you may well see it in this kind of form, but sometimes you'll also see it in the form of what's called a Sankey diagram. And where people go wrong with Sankey diagrams is they get really confused when there's no numbers. Okay, so for example, if we draw a basic Sankey diagram here, sometimes you have one bit of useful energy going out, sometimes you might have a couple of bits of wasted energy. It doesn't really matter how they give it to you in the exam, but you will have two parts of the diagram showing, one showing energy out and one showing wasted energy out. So for example here, if we took the idea of a kettle, this could be the useful energy, which is the heat, and they tend to label these, and this could be the wasted energy, which in the case of a kettle could be something like sound. So all you need to do with the Sankey diagram is look at the widths of the bars that are coming out. And if there's no numbers, that's absolutely fine, because we just have a look here and see the width is 2 squares. And then we have a look at the input energy, which is the width of the whole thing, and we see that is 4 squares. So to calculate our efficiency, we just do 2 divided by 4 times 100%, and that will give us 50% efficiency. Or you might see it where there are numbers on as well. So for example, over here on this diagram, rather than doing it without numbers, with just squares, you could have numbers on this diagram here. So we could have an input energy, for example, of 100 joules, and we could have a useful output of 50 joules, and they might give you the numbers. And in that case, you would then do 50 divided by 100 times by 100, and that will get you 50%. Okay, so whether they've got numbers on or not, do not be worried about it. It's exactly the same calculation. I've had people come out before of an exam saying the Sankey diagram was wrong, they didn't give us any numbers. Don't worry about that. If they don't give you any numbers, just count the squares. So with these Sankey diagrams, you want the with these appliances, you want the most useful energy going out. So if you see a Sankey diagram with a really big bar for the useful energy, and then a really small bar for any wasted energy, then that is going to be a really good appliance, because most of it is useful and then there's a little bit of it wasted. Okay, moving on, we're going to talk about types of energy, and we're going to first of all look at non-renewable energy. These are energy types that will, sources of energy that will run out in our lifetime. So these are things like fossil fuels like coal, oil and gas, coal being made from plants, and oil being made from dead marine animals, and so is gas. And these can all be extracted and used to generate electricity, and this is what we most rely on for our fuels. And of course we can use oil straight in our car and things like that as well. We've also got nuclear energy as well. You've got some radioactive materials like uranium and plutonium, and those are radioactive fuel sources that release energy, and those can be used in the power station as well to release energy. So we need to remember that all of these are non-renewable. Even though we've got quite a lot of nuclear, that will also one day run out. So we can use these fuels to generate electricity in a power station. And I'm just going to show you the fossil fuel power station and the nuclear power station here. So this one runs on coal as an example. The important thing about these is they have to be close to some sort of river or some sort of water source. So that's why power stations are often on the coast. And you can see in here, if you look at the water is going into here, into the boiler, where it is being heated up. It is being turned into steam, and that steam turns a turbine, and that turbine will turn something called a generator, which is down here, and that's how the electricity will be made. So you've got that basic link of a boiler, which is using the coal to burn and heat the water. It turns a turbine, and that turns the generator, and you've then got your electricity, which is transported on the national grid, which we'll come to later. But those are your basic setup, and you need to remember that all in this process you're heating water to make steam, and that turns the turbine. Now exactly the same principle happens in a nuclear power station, but you get this domed shape structure in it instead, and this is where the nuclear reactions go in. So inside this dome shaped, and you'll recognise it's slightly different to the fossil fuel one, there'll be a reaction vessel, and in here you will have your radioactive material like uranium or maybe plutonium. And in this nuclear reactor, this will be giving off energy, but again that energy will be used to heat water, which will be created and turned into steam, and that steam will turn a turbine, that will turn a generator, and you'll generate your electricity. So it has this exact same process. It is just in this case that radioactive material is decaying and releasing energy to heat the water in the boiler, whereas over here the fossil fuels are being burnt to heat the water in the boiler. But exactly the same setup to produce the electricity. And in the UK we use nuclear and fossil fuels plants a lot still. You can see here that we've got a collection of cold water as well, which is used for this system. Now this can be controlled as well. You don't need to go into detail for this P1, but it will come up in P2. You can control the rate of the reaction in these nuclear power plants using these things called control rods. So moving on, as well as non-renewable energy, you can also get renewable energy. Okay, so renewable energy will not run out. And that's really good for us, and because we can keep using those energy sources again and again and again. And all of these are examples of renewable energy: solar, hydroelectric, hydro using water to generate electricity, geothermal using heat from the earth, like geography. Try and break down these words to help remember them. You've got wind energy, got wave energy, tidal energy, and also biofuels. Biofuels, if you remember, biology is the study of living thing. Biofuels are fuels made out of living things. And all of these do the same thing. They turn a turbine, which turns a generator, which generates electricity. So just the same in the non-renewables did it in a power station, these do exactly the same thing. So you need to remember these 3 steps. Now, some of them are pretty obvious. So solar, obviously using the energy from the sun and solar panels. Wind, using a wind turbine, and that wind is straight away turning the turbine to turn a generator to generate electricity. Tidal waves, you would have the movement of the tide in and out, and they would go through a turbine. And the waves, well, not the waves, but the whole tide will move through that turbine and turn the turbine, which turns a generator, which generates electricity. Now, biofuels can come in a number of ways. It could be perhaps burning animal waste, or it could be perhaps burning ethanol, which is made by a biofuel process that came up in C1. So maybe using ethanol, which has been made by fermentation, or it could be burning some kind of plant material or some kind of vegetable oil to make your fuel. Okay, so I'm going to go into a couple of these in a little more detail. First of all, I'm going to look at a wave machine, because this is the one that people get wrong quite a lot of the time. They think that the water is pushing the turbine. Now, what normally happens in a wave machine is that the water goes up and down into a chamber and it compresses or squashes air. So as you can see here, the wave went up into this chamber, all the air particles in here would be squashed together, and this would turn the turbine. So just bear that in mind. If they show you some sort of diagram of this, it's the air in the wave machine that's turning the turbine, not the action of the wave itself. And sometimes you get quite a complex diagram like this, and people haven't thought about this in enough detail. So the air turns the turbine, which, you've guessed it, turns the generator, which generates electricity. Another one I want to go in a little bit more detail is geothermal. With geothermal, again, we're using the heat of the earth. So naturally, in some places, we can access the heat from further down into the earth, where it's going to be really hot, and there's lots of hot rocks. And what we can do is pump cold water down to those hot rocks. That will be naturally heated by the hot rocks, and it will come back up as steam and hot water. And hopefully you've got the clue now that the steam will then turn the turbine, which will turn the generator and generate electricity. So you might see a diagram a little bit like this that you need to relate to geothermal. The other one I want to go in a bit more detail is hydroelectric energy. So hydro, meaning using water to generate electricity. And these are the ones where you'd have a large reservoir. So a reservoir is just a big collection of water. And the water would be allowed to flow down the reservoir, turn a turbine to turn a generator and generate electricity. And it would then collect in the lower reservoir there. Now, linked into this, people tend to miss this out of their revision quite a lot, is the idea of pumped storage. And what that is in some of these hydroelectric power stations, you will have a channel which is going back up to the top reservoir with a pump in the middle to pump the water up. And this means that the water can be stored up in this high reservoir. So if you really need it really quickly, then you can open this gate and generate more electricity this way. So unfortunately, you have to use energy to pump it up there in the first place, but it just gives an extra supply of electricity when needed. Okay, so they tend to use any spare electricity that they've got left over at night to run this pump and then store the energy technically up here for when they need it later on in the day. Because you've got this idea of supply and demand, you've got a demand for electricity, which will change throughout the day. In the daytime, you'll have quite a high demand for electricity, whereas for obvious reasons at night time, when all of our lights are off and we're not using our computers and everything so much, the demand for electricity goes down. And we've got to match that with the supply, okay? So we need to make sure that we're supplying people with electricity in the day, and perhaps at night, any excess electricity we've got, we can use to store the energy up here for later on. Okay, one thing also that people tend to miss off their revision is carbon capture and storage. So this is the idea that when we burn lots of fossil fuels, so for example, coal or oil or gas, when we burn these, we are releasing CO2 into the atmosphere, and this is leading to global warming. So the idea of carbon capture and storage is that once you've taken oil or gas out of the ground, so far underground, the idea is that actually you'd end up with an empty chamber underground. So what scientists are trying to do now is fill this chamber with carbon dioxide. So carbon capture and storage. So rather than releasing the carbon dioxide into the air, the idea is that they would capture that carbon dioxide and pump it and store it underground. Okay, probably for another generation to try and solve that problem with all the carbon dioxide. Okay, so this is an idea to reduce global warming, and it's called carbon capture and storage. Okay, with setting up a power station then, you might want a power station for your local area or for a new island or something like that, and you need to think about whether it's best to have a renewable power station, so maybe one that's run by wind or hydroelectric or something like that, or whether you would want a non-renewable power station. So in the exam, they might give you a scenario of a certain city or a certain place or an island that needs electricity, and you need to think about the most appropriate one for that place. So in your decision, you need to think about, is the energy going to be reliable? So for example, wind is not very reliable. Okay, and things like solar, that's not particularly reliable because it's not going to be sunny all the time. But fossil fuels are really reliable, and you can run those all of the time, continuously. You've got to think about things like the cost. So for example, what is the cost of coal or oil or gas at the time, and which would be the best one to use? Or maybe the costs in setting it up. So actually, building a massive hydroelectric dam is really pricey. Okay, so would this be the best one to use for that area? Maybe they'll give you some costs in the exam for building a wind turbine. Now, wind turbines themselves are pretty pricey compared to, for example, a solar panel. So is it necessarily very good to do that? Decommissioning means the time taken to take a power station apart, and for nuclear, this is really costly and takes a long time. So you've got to bear that in mind when you're choosing the right power station. Location is important as well. For example, if you choose a wind turbine, it's got to be windy, so you've got to think about the weather. If you're choosing solar energy, it's got to be somewhere that's going to attract a lot of light for a big part of the day. If you're choosing hydroelectric, you're going to need somewhere near a big water source or somewhere where you can build a massive hydroelectric dam. So you've got to bear that in mind when you're talking about location, especially in terms of weather, or maybe you'll have to have it close to water because you need to be able to generate the steam and generate electricity from that. Of course, there's always environmental concerns. Things like hydroelectric would have a massive impact, but maybe putting a few solar panels on a roof to help out a local community would not have such a big impact. So that's got to be something that you bear in mind when you are setting up your power stations as well. And obviously, you've got the CO2 that's released by fossil fuels. And they also can release sulfur dioxide as well, which will cause acid rain, and CO2, which is causing global warming. And you've got really large setups like the hydroelectric dam. Obviously, that's going to have a massive impact on the environment around it as well. So just things to bear in mind. Massive wind farms spark a lot of controversy as well. So all of these things here, you'll have to bear in mind when deciding which power station to set up for a particular area. Okay, and then once you generated your electricity, you need to give it to all of the houses, and you do that through the national grid. And the national grid is a series of cables and transformers. Okay, so we don't class the power stations in the national grid. We just class the cables and the transformers. So you don't need to know too much about transformers for your exam. You just need to know that one steps up the voltage and one steps down the voltage. So these here are the transformers. So one steps up the voltage and one steps down the voltage. And we'll discuss why in just a second. So the two types of cables that you can have then that are transmitting the electricity are overground cables and underground cables, and they might ask you to compare the advantages and disadvantages of both of them. So the overground cables are what we use most often at the moment, and we do that partly because they're low cost compared to the underground, which are high cost. The ones that are overground, they need a lot of maintenance. Okay, so this is positive, but a negative is that they need lots of maintenance, and you'll always see people working on these power lines and cables, whereas these ones here are low maintenance. Because they're underground, they shouldn't be affected too much by the weather and things like that. So these ones, because they're need a lot of maintenance, actually one advantage is that they're easy to get to. So if you need to fix a fault, they're easy to fix, whereas the underground ones, because they're buried deep underground, they are very difficult to fix. If anything goes wrong, they'll have to dig up a massive piece of the land to fix them. Things to do with eyesore, these can cause an eyesore, okay, if they, for example, across the New Forest or across a site of natural beauty, you don't want these overground cables spoiling the scenery. Whereas if you put them underground, you can't see them, okay, so they're hidden away. The overground ones are also affected by weather, so that doesn't make them particularly good, but the underground ones, because they're away, they're not affected by any changes in weather. What else have we got? So overground also are less reliable because of the fact that they can be affected by the weather, and there's quite a lot of faults on them normally, whereas if they're hidden underground, they're protected and they are more reliable. Finally, in terms of cost, these are really easy to set up, and that links into their low cost, so easy to set up, whereas these ones are quite difficult because you're going to have to dig up the whole ground as well. And obviously this will have a bigger effect on the environment because you're going to have to dig up massive pieces of ground. But once they're under there, then the environmental impacts are going to be quite low. So you might get a comparison between these two. There's loads of things that you can say about them. And the one thing we just need to cover is why that voltage is stepped up. And the reason is because when you step the voltage up to about 440 kilovolts, or about around 400,000 volts, you're going to have a low current. Okay, so a higher voltage on the power lines means a low current, and that means that less energy is wasted. And that's the same as saying that they will be more efficient. And the reason for that is, if you think about the wires going through those cables as being loads of metal atoms here, then electrons are going to be flowing through those wires. And if there's a big current and loads of electrons going through, it's going to heat up the wire, and then energy will be lost as heat because of that big current through there. So to prevent that, what they do is they make a really small current and a high voltage, and therefore less energy is lost as heat, because you don't want loads wasted in heating up the environment. You want it all to go to your homes. Okay, so very well done if you've kept up so far with the energy. Now feel free to stop the video there and have a break, because I am going to be going on to talk about waves, but you might want to do this session in a couple of doses. So feel free to stop, take a break, and then come back and concentrate on the waves topic. Now for waves, there's a few properties that we need to know about. So one of those is the wavelength, which is measured from the same place of the wave. So it could be measured from there, or we could measure it from here or here. It'll be exactly the same measurement, and that is measured in meters. And we also have amplitude as well. It's really important to measure the amplitude of the wave from the midpoint up. And we'll talk about these in a little bit more detail when we talk about sound waves and what they mean. The other property of the wave that we need to know about is frequency. And frequency is measured in the number of waves per second. And that is measured in something called hertz, capital H, little z. So if we had 5 waves per second, for example, we would have a frequency of 5 hertz. And in the exam, they sometimes are cheeky and give you it as waves per second. So just bear in mind that that is what frequency is, the number of waves per second. So if we were to draw a wave, this would be a high frequency wave, and this would be a lower frequency wave. And frequency and wavelength are linked. If you have a short wavelength, that means high frequency. And if you have a long wavelength, that means low frequency. And if you draw these out on any white space that you've got on your exam paper, that will help you out loads, because you can start to link the idea between wavelength and frequency. Okay, if we're talking about amplitude, this would be a wave with a low amplitude, whereas this would be a wave with a high amplitude. Okay, so just bear those properties in mind as we go through the topic. So there's 2 ways that we can generate waves. We can have a transverse wave, or we can have a longitudinal wave. And there are 2 different types of wave. Transverse waves are all of the ones in the EM spectrum, so the electromagnetic spectrum, including light waves, and longitudinal waves are examples of sound waves are example of those type of waves. And it all depends on 2 things. It all depends on the direction of the vibrations, okay, and it depends on the direction of the energy. Because this here is an example of a longitudinal wave. You can see that the person is moving the spring backwards and forwards in this direction, and the energy of the wave is going to be transferred in this direction as well. So we can say that the direction of the vibrations is parallel to the direction of the energy. This comes up really commonly on the exam. So the direction of the vibration is parallel to the direction of the energy. On the other hand, you've got a case where someone's moving a wave up and down, moving the spring up and down, and the energy is traveling in this direction. Because even though they're moving up and down, the energy transfer is still in this direction, so the wave gets transferred to here. So in this case, we say the direction of the vibration is perpendicular to the direction of the energy transfer. And you can see this here because we're moving up and down, and that's perpendicular. Perpendicular just means at 90 degrees. So if you can't remember that, you can write down 90 degrees, but this is better to remember perpendicular. So this is a transverse wave over here, and this is a longitudinal wave. So with a slinky like this, with a spring, you can either make a longitudinal wave with it, like this one here, or you can make a transverse wave by bouncing it up and down. So really important key terms about the direction of the vibrations and the direction of the energy. And that brings me to an important point. They sometimes have this kind of gap fill. So all waves transfer what? And the answer is energy. All waves transfer energy. Also, when we talk about this wave here, I just want to bear in mind, because I might not have a good diagram coming up, you can see here in this wave, there are areas where the spring is compressed. That is called an area of compression. And this here is called an area of rarefaction. So in a longitudinal wave, you've got two different areas, one of compression and one of rarefaction. So here in compression, the particles are close together, and here in compression, the particles are far apart. So bear in mind those two different areas as well. Second thing to bear in mind is calculating a wavelength on this type of wave. So this one's easy. It's just like our properties diagram we showed earlier. We'd calculate the wavelength here. Whereas for this longitudinal wave, we'd calculate it from the same place on one compression to the same place in the other. So for example, if we take the middle of this compression and the middle of this compression, this would be our wavelength. So just bear that in mind. Sometimes they'll ask you to calculate the wavelength on these kind of waves as well. Okay, so first thing that I want to look at that waves do is reflection. So I'll use an arrow to show this. We've got a wave coming in here to the mirror, and that wave will be reflected out in this direction over here. Really importantly, in the middle, we put a line at 90 degrees to the surface, and this is called our normal line. And this is a dashed line. We always have to draw it in a dashed line because it's an invisible line. It doesn't really exist, but we draw it in there, and it helps us measure our angles. So this is the incident ray, the ray that's going in, and this is the reflected ray. So both transverse and longitudinal waves do reflection. For example, the reflection of sounds is an echo. Okay, and we know a really important thing about reflection, and that is the law of reflection. And that is that the angle of incidence equals the angle of reflection. Super important law that we need to remember, but sometimes people forget what the law of reflection is, even though they know this rule. So to measure the angles then, we've got this angle here between the normal and the incident ray, and this here is our angle of incidence. And then over here we have our angle of reflection. And reflection's nice and easy. If this angle is 40 degrees, then this angle here is also 40 degrees. And make sure that degrees is written like this, and you don't get it confused with temperature, which is degrees C. Okay, so this is the degree symbol for the angle. So that's reflection. The next thing that I want to look at is refraction. Refraction is when light bends when it goes through a different medium. Okay, we kind of say bends, but it's better to say changes direction. Okay, so when a wave changes direction, because we remember that waves, light for example, travels in straight lines, so it's better to say changes direction rather than bend. So when a wave changes direction when it goes through another medium. A different medium. Now, all medium is a different material, but you'll probably see that word medium in there, so you need to get used to it. It just means a different material. For example, if we have a light ray that starts in air, goes through a glass block, and comes back out of air, we might have something that looks a little bit like this, where you have a wave going in. Okay, we need to draw our normal line on to help us. That wave will then bend towards the normal. Okay, and it will go a straight line through it out there. And then it will come out to the other side. So we'll draw our normal on here to help us. Make sure that's straight in your exam when you do it. And then it will come out of the other side. And it comes at the same angle that it goes in at. So I'll approximately do it about there. So if we look at this now, we've got the ray coming in from the air to the glass block. This angle here is going to be bigger because at this point here, the wave bends towards the normal. Or if we're talking about light, sometimes we call this the light ray. It bends towards the normal, so this angle is smaller than this angle. And then as it goes out again, it bends away from the normal. Okay, and then this angle here, I'll call this X, is exactly the same as Y. So as it goes from air into glass, it will slow down, and that will cause it to change direction. And then as it goes out of the glass into the air again, it will speed up because this glass here is denser than the air, so it slows it down, and then it speeds up again as it goes out of the air again. Now you might see this in terms of, for example, an exam, they might talk about light going through a water bottle. A really difficult one that I saw one time was when they had the light ray going through the water bottle a little bit like this. Okay, so just bear that in mind, and the reason why they had it going through like this was because if you have a look here, you draw a little line here, the light ray is actually going in along the normal. Because if we draw a tangent to that line, this is probably more in the higher paper, but if we draw a tangent to that line there, the light ray is actually going in at 90 degrees. And when that happens, when the light ray goes through a different material at 90 degrees, it will go straight through. So if the light ray goes along the normal, it doesn't refract. And it doesn't change direction. So just bear that in mind. And in this particular question, you were asked to finish off the ray diagram, and you would have had the light ray coming out down here. So bear that in mind. That comes up quite a lot, that if the light is traveling along the normal, it doesn't refract. But in this case, you would have the case where the light goes in, changes direction, slows down, and then speeds up again and changes direction as it goes out. So that is refraction. Next, I want to look at diffraction. Diffraction is when the light waves spread out as they go through a gap. So the spreading of light waves, or any wave, so the spreading of waves as they go through a gap. Could be through a gap, or it could be over an edge, like a mountain or something like that. So the key is, if you have the lights, the waves coming in like this, to measure the wavelength, we'd look between these two lines, and that would tell us the wavelength of the waves going through. Now with diffraction, as the waves go through, they will bend through this gap. There's a few things that are important when you draw this diagram. First of all, the wavelength that's on this side has to be the same as the wavelength that's on this side. So you need to be careful when you're drawing that in your exam. An important thing to note that if this wavelength here is a similar size to the wavelength of the gap, then they will diffract a lot. So if your wavelength of the wave is similar to the size of the gap, sometimes they use the word magnitude of the gap, okay, so the size of the gap, then you're going to have lots of diffraction, lots of spreading out. On the other hand, if you have this scenario here where actually the wavelength is a lot shorter than the size of the gap, you're going to have very little diffraction, and you might just be getting some spreading out at the edges as it goes through. Okay, so just bear those diagrams in mind, and this bit's really important and a common question when it comes to diffraction. Okay, moving on then, we're going to look at an image in a plane mirror. Doesn't come up very often at all, but it is something that people forget when it comes to an exam. When an image is projected inside a mirror, it is called a virtual image. So for example, if we are here looking at the mirror, and this is the mirror here, we would see that candle behind the mirror. And because it's not a real image, because the candle isn't really behind the mirror, we would call this a virtual image. But that virtual image is also upright, so it's not flipped up like you would see in a camera, but it's upright, and it is also the same size as the original candle. Okay, and the only thing that you'll see is that the left and the right side swap. Okay, it's difficult to see in a candle, but the left and the right sides of that candle swap, and this is called a really difficult term. It's called they are laterally inverted. Okay, so these are the kind of things that come up in foundation as far as looking at the image in a mirror. The idea that it's virtual, upright, the same size, and perhaps that the left and the right hand sides are swapped, which is called laterally inverted. If you're doing higher tier, I'd really look to be able to draw these images. So my top tips are, you'll probably get this side of the mirror, and the first thing that you do is draw your image over here, and then you want to draw one line which is dotted to the mirror and then straight to the eye, and then another line from the top which is dotted to the mirror and straight to the eye. Now these need arrows on them. It's really important that the light is going to the eye, like this, and not coming out of the eye. So don't forget that the reason that you see something is because light goes in the eye and not because you've got these eyes that are amazing at shining light. So have a look for a couple of practice questions for these if you are doing higher paper, just in case it does come up. But it's not very common that it does come up. Okay, moving on to the electromagnetic spectrum. Feel free to have a break and come back if this is going too quickly for you. But the EM spectrum, we need to remember the order of the waves in the electromagnetic spectrum, and you've probably got your own little rhyme to remember it. But we need to remember G, X, U, V, I, M, R. Okay, where you've got gamma, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Now, what I really strongly recommend you to do in exam is write down your letters that you've got. Okay, so write down G, X, U, V, I, M, R, and then draw a wave to show the frequency and the wavelength. So if you do straight away in your margin or anywhere on the white piece of paper, draw a wave like this. It will remind you then that gamma are the rays that are short wavelength. It will remind you that they're high frequency. compared to the ones down here, the radio waves, which are long wavelength and low frequency. So just drawing that little diagram will help you remember it. Now do bear in mind in the exam that they could have this the other way around. They could have radio waves over here and gamma rays over here. So just bear that in mind. And also people forget this bit, the fact that visible light is actually split up into several different colours. Okay, it's split up into red, orange, yellow, green, blue, indigo and violet, or Roy G. Biv. And red here, red light, is next to infrared, and violet light is next to ultraviolet. So this comes important later when we're talking about redshift in the spectrum. So all electromagnetic waves travel at the same speed in a vacuum. A vacuum is somewhere where there's no particles. That will come up in the vacuum flask and conduction and convection earlier in the topic. So vacuum, there's no particles, and all EM waves travel at the same speed in a vacuum. And you don't need to remember this, but that speed is 3 × 10⁸ meters per second, or 300 million meters per second, which is the speed of light, and is also the speed of every other electromagnetic wave in the EM spectrum. You also need to remember one little fact, and that's the length of the wavelengths, and they range from 10 to the -15 meters, really, really tiny wavelengths for gamma rays, up into 10 to the 4 meters, or 10,000 meters. So one little fact for foundation and higher that we need to remember is that they range from 10 to the -15 to 10 to the -4 meters. So all of these waves are carrying energy, just like all waves do. And these ones here, because they're the high frequency, they're also the high energy, because they transfer most energy, because they've got a high frequency, loads of waves every second, whereas the radio waves are the low energy ones. So lots to remember for the EM spectrum. If you remember the order, that will help you. And if you write down or draw down a wave like this, that will also help you remember these properties associated with it. So there's a few dangers that are associated with electromagnetic waves. For example, you've got ultraviolet, which can cause skin cancer. You've got microwaves, which are linked to their use in mobile phones. And there's associated danger with the mobile phones. There's no evidence that mobile phones are dangerous, but people have the idea that if you've got the mobile phone right next to your head, then that may, just like a microwave warms up food and excites the water particles in food, there's worry that the use of mobile phones next to your head could damage the cells in your brain. But there is no evidence for that. So they might ask you whether there's any evidence. You just remember there's not. Also, things like infrared radiation could cause burns. So infrared radiation is from grills and things like that. There's no major dangers associated, obviously, with using a grill or a toaster. But if you were to touch it, it would burn yourself. And the major danger comes with gamma rays. They can cause cancer. They're really high frequency, high energy. They can cause cancer, but we'll look a bit later on if they can actually prevent cancer and kill, not prevent cancer, sorry, but they can kill cancer cells as well. So yes, they can cause cancer, but also we're using them to kill cancer cells as well. X-rays are obviously got their associated risks with them. If you're a nurse, you'll be wearing a lead apron to protect you, because you don't want to get a serious dose of X-rays, because again, these are at the higher energy level of the spectrum. So there are fewer dangers associated with it. The waves near the gamma end of the spectrum are more dangerous than those radio waves at the lower end of the spectrum. Okay, so they're more dangerous. Whereas radio waves have very few risks associated with them, but gamma rays right at the top can cause cancer. So uses of these electromagnetic waves then, a lot of them are used in communication. So first of all, radio waves can be used for radio and TV communications. So they travel really long distances because they've got really long wavelength. They can travel long distances. You've got short radio waves that can reflect off of the atmosphere. So if you had a transmitter down here, the short radio waves would go up and reflect back off of the atmosphere to perhaps a house over here. And you've got the long radio waves, which will travel further and bend round mountain ranges and things like that and travel further round the Earth. So it's the short ones that reflect off and the long ones that bend round the Earth. With microwaves as well, these are really used for communication. So as well as heating food, they're really important for communication. They are the ones that communicate with satellites. So they are used for mobile phones and GPS signals and things like that. So these will actually go out of the atmosphere and they will communicate with satellites out of the Earth. So if you've got the Earth here and the atmosphere around it, any microwaves can go out to a satellite and then they will reflect that signal back to somewhere else on Earth. So these are really important, these microwaves, and they're important for a lot of our day-to-day life and the things that we use. So as well as that, you've got other uses of waves. So you've got infrared waves, and these are used for remotes. So not really linked into communication, but these are used for remote control. Technically, they're communicating with television, and they're also used in optical fibers as well, which will be related to communication. So infrared and visible light can be used in these optical fibers. And what happens is a pulse transmitter will send out the infrared radiation, and that will be passed along the wire to a receiver. So lots of communications in the broadband network and things like that use these optical fibers, and they tend to have either infrared or visible light to communicate and pass along a signal. Final thing then is the visible light. Not in terms of communication, so I'll just put this separately, but this is used in photography and cameras. So this could be speed cameras, for example, the light reflecting off your car and going into the camera lens to take a photo of you, or obviously handheld cameras and things like that. So lots of things that these EM waves are used for, lots of things that day to day we use them for, especially microwaves. Without those, we wouldn't have mobile phones and we wouldn't have satellite TV or satellite communication. So just a few more things to finish on waves, not too much left to do. First of all, we'll talk about sound waves, and where sound waves comes important is looking back at the properties of waves when we talked about amplitude and when we talked about frequency. With sound waves, a low amplitude means a quiet wave, whereas a high amplitude means a loud wave. So the amplitude tells us whether the sound wave is quiet or loud. With frequency, this tells us the pitch. So with a high frequency, this means high pitch, and with a low frequency, this would mean low pitch, so a lower sounding sound. And the way sound waves are generated, we mentioned briefly before that they are longitudinal wave, and they are passed on by vibrations of the air. So in case of a speaker, the speaker's skin will be moving backwards and forwards, and the air in front of that speaker will then be vibrating backwards and forwards, and it will transmit a wave of vibrations in this direction. And because the air particles are vibrating in this direction and the energy is transferring this way, we, again, just to repeat myself, we say they're parallel. The vibrations are parallel to the energy transfer, and the wave of energy is passed on. So sound, is all to do with the vibration of air. Okay, in relation to sound, we get something called a Doppler effect. And to explain what that is, we just need to remember the idea that if a car is on, okay, it will be generating sound, and those sounds will be coming out of the car in all directions as a wave. So we can draw bands of waves coming out of that car. And if that car is still or stationary, those waves will be coming out equally on all sides. And they will still be coming out equally if the car is moving. But we have a special effect that happens when the car moves. For example, if the car moves in this direction, even though the sound is still being generated with the same frequency, the car moves into the sound waves and pushes them together. So if the car was moving into this direction, the sound waves would look distorted and look a little bit like this, as the sound is being compressed at the front as the car is moving into the sound waves that it's producing. So actually, if this car stopped, it would still be producing sound waves like this, and the exact same frequency is being produced, but now the car is moving into its sound waves that's generated in front, and it squashes them all together. And what happens with this is that here, if you were stood at the front of the car, you would hear a different sound than if you had stood behind the car because of these waves. So if you were stood in front of the car, you would hear these waves, which are closer together, so they're a high frequency and therefore a high pitch. We might need to talk about these in terms of wavelength as well. So they're short wavelength, which you can see by measuring them here, a high frequency and therefore a high pitch. Whereas if you were behind the car, you would hear these wavelengths. So you'd hear a long wavelength, and that means a low frequency and therefore a low pitch wave, okay, from behind. And this phenomenon is called the Doppler effect. And this is the reason that if you would stand by a race course, for example, and hear the Formula One cars going past, you would hear the pitch change. You would hear something like this, where at the front you'd hear that high pitch, and behind you'd hear that low pitch. Okay, that's why you get that sound, because at the front you'd hear high frequency waves, and at the back you'd hear the low frequency ones. The same if an ambulance was moving past you at high speed as well. Now remember this effect, because a very similar effect happens in light, and when it happens with light we call it red shift. So let's imagine the same thing, but this time this is a galaxy and this is Earth, and the galaxy is emitting light, okay, which I'll just draw as circles around that galaxy. So I'll just delete those, I'll just do it in a red pen to draw the circles of light coming out the galaxy. Now normally if we had our galaxy, the circles of light would be going in all directions, but in this case, because our galaxy is moving away from us, we see this kind of thing coming from the galaxy. So we see these light waves again bunch up over in front. Oops, sorry. We see these light waves bunch up in front. Of course, it's moving this way, and spread out further away from the galaxy as the galaxy is moving in and compressing those light waves that it's generated. I'm not drawing this very well, but at the back you would get them spacing out, and at the front you'd get them going very close together. So swap that bit. So here it'd be like standing behind the car before. You'd get your long wavelength and low frequency light waves. Okay, and at the front you'd get your high frequency, short wavelength light waves. Okay, so this galaxy is producing light in all directions, but because it's moving, we're getting a different picture from if we were to look at it behind as if we were to look at it at front. And what that means is that on Earth, the light that those galaxies are showing appears to be a little bit red, and it's shifted into the red end of the visible light spectrum. If you remember before, we got visible light, which goes all the way from violet to red. Okay, if we fill in the colours, red, orange, yellow, green, blue, indigo, violet. And the light coming from this galaxy will appear to be a bit redder, where it's shifted into the red end of the spectrum. And we call this phenomenon red shift. So if you're someone on Earth detecting the light coming from that galaxy, you will see that it's shifted into the red end of the spectrum. And you will see that from these absorption spectra diagrams. So this is an example of an absorption spectrum. And you will see if this, for example, was the light coming from our sun, the light coming from a distant galaxy, because it's moving away, would be red shifted. So this would, for example, be the absorption spectrum from a galaxy which is moving away from us, and this would be our sun. This, on the other hand, would be a galaxy moving towards us, because all the lines have shifted in the other direction. So this would be a galaxy moving away, and this down here would be a galaxy moving towards us. Okay, so in the same idea of the sound waves, this kind of effect happens with light, and we call it red shift, because what we are seeing is the longer wavelength. If you remember how visible light sits in the spectrum, you've got the longer wavelengths, which are the red light, and the shorter wavelengths that are visible light. So in front of the galaxy over here, you would see this kind of end of the spectrum, whereas behind the galaxy, what we see is the light is shifted into the longer wavelengths, so we see a redder light. We see this red shift. And this provides evidence for us that galaxies are moving further away. So we are in the galaxy the Milky Way, and this redshift provides evidence that galaxies are moving further away from us. And we'll link that into the Big Bang now. So final slide then, just looking at the origins of the universe, we're going to relate the red shift to Big Bang. So we said because we can see the light from distant galaxies is shifted into the red end of the spectrum, we can say that red shift provides evidence for the Big Bang. And all the Big Bang is the idea that at one point, all of the mass of the whole entire universe, all of the galaxies and all of the planets, it's really difficult to get a head around, but it's the idea that all of that was concentrated in one space, and then a massive explosion caused all of the matter and the energy to be spread out. And the idea now is that the universe is still expanding. And we get that from our red shift, okay? The red shift tells us that the universe is expanding and the galaxies are moving further and further away from each other. Now, the reason this provides evidence for the Big Bang is because if galaxies are now moving away from each other, then if we were to look back in time, we would realize that actually, if we reverse this idea, that they must have once come from exactly the same place. So that's what they think. That's how they link redshift to Big Bang, because they're saying if now we're seeing these galaxies moving away, if we reverse back in time, we'd see that actually they'd all come from one original place, and that must have then caused an explosion, which they call the Big Bang, to give the universe as we see it today. But they also believe that the universe is still expanding. because they're still seeing that redshift. They're still seeing those galaxies move away. Now, Big Bang is linked to something called the CMBR. CMBR is cosmic microwave background radiation. And this radiation is seen all over the universe. So just depict the universe like that. This background radiation is in all directions across the universe. And the only thing that can explain the CMBR is the Big Bang theory, this idea of this massive explosion spreading that radiation across the universe. So the Big Bang is the only idea that can explain the CMBR, the cosmic microwave background radiation. Okay, so this is linked to the CMBR, and this would have been released just about the time of the Big Bang. Now, the other theory of how life began is this steady state theory, and the steady state just essentially means that the universe has always been like steady state theory. So I doubt they'll ask much about that in the exam, but that is another theory that people believe, that the universe has always been like it is now, and obviously that will link into religious views. But with the Big Bang theory, we're talking about 4.5 billion years ago, a massive explosion causing the universe to still expand. And these galaxies here that are moving far away, they're showing more and more redshift, and the galaxies right on the boundaries are moving fastest and showing more redshift, which is providing us evidence that the universe is still expanding. Okay, so that's everything that I wanted to cover for the second half of the P2 topic. Apologies there weren't any questions in this Hangout. I'm running out of time to do those, but hopefully that covers all of the information that you'll need and will help you along. What I recommend is that you use this in a combination with loads of other revision tools, including your revision cards and doing past papers, looking over these videos again if there are any points that you missed out, and hopefully that will stand you in really good stead for the exam. Now, the night before the exam on Tuesday, I will be doing another revision Hangout, which will be 7 till 8, just covering some key exam tips and some good exam practice. So hope to see you then.